Space weather is a term that encompasses various phenomena that occur in the space surrounding Earth, driven primarily by the sun's activity. These phenomena can have wide-ranging effects on Earth and its technology, and even the lives of people who rely on satellite systems for communication, navigation, and weather forecasting. The Sun, our closest star, is a dynamic and constantly active force in the solar system. It isn't a steady, calm presence. It periodically burps, expelling massive amounts of energy and particles into space. These bursts of energy, known as solar flares and coronal mass ejections (CMEs), can send shockwaves through the space environment, creating what we call space weather. This space weather is the result of the sun's magnetic field interactions with particles in the solar wind, which is a continuous flow of charged particles from the sun, and the Earth's magnetosphere, which shields our planet from the full brunt of these energetic particles. When the sun releases these bursts of solar radiation and charged particles, they can disrupt satellite operations, communications, navigation systems, and even power grids on Earth. The effects of these solar events on human-made infrastructure are significant, and understanding the mechanics of space weather is crucial for modern society to safeguard against its most severe impacts. Solar flares are sudden bursts of energy in the form of radiation, released when magnetic fields on the sun's surface reconnect in violent, explosive ways. These flares release huge amounts of energy, spanning the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Solar flares can last from a few minutes to several hours, depending on the size and intensity of the flare. During these flares, the sun releases an enormous amount of high-energy radiation, including X-rays and ultraviolet light, which can influence space weather in a number of ways. The most immediate impact of solar flares on Earth is on communication and navigation systems. The high-energy radiation from solar flares can ionize the Earth's ionosphere, disrupting radio signals that travel through this region of the atmosphere. This can lead to radio blackouts, particularly on the sunlit side of the Earth, and can interfere with high-frequency communications, which are vital for aviation, maritime operations, military communications, and emergency services. Additionally, solar flares can affect GPS signals, causing inaccuracies in positioning and navigation systems that rely on satellite signals. For instance, GPS accuracy may be reduced or temporarily unavailable, making it difficult for pilots, sailors, and even autonomous vehicles to navigate with precision. On a larger scale, solar flares can also contribute to the heating of the Earth's upper atmosphere. This heating can cause an increase in atmospheric drag on satellites, causing them to lose altitude and eventually deorbit if not properly adjusted. The energetic radiation from flares can also cause damage to electronic components in satellites, leading to malfunctions or even total failures. The radiation from solar flares can interfere with satellite electronics by causing minor issues like signal degradation or more severe consequences like circuit failures, damaging sensitive components like solar panels and communication systems. The charged particles from solar flares can also accumulate on satellite surfaces, potentially leading to surface charging, which can damage satellite electronics or even create dangerous sparks. While solar flares may not directly destroy satellites, they can significantly reduce the lifespan of these devices and complicate their operations. These space weather events can also create significant risks for astronauts aboard the International Space Station (ISS) and other spacecraft, as the energetic radiation can increase the risk of radiation sickness and pose a danger to crew members' health. Coronal mass ejections, or CMEs, are another form of space weather that can have even more severe effects on Earth and its infrastructure. A CME is a massive burst of solar wind and magnetic fields rising from the sun's corona and being released into space. CMEs carry with them a significant amount of plasma-charged particles such as protons, electrons, and heavier ions, along with magnetic fields. These CMEs can eject billions of tons of material into space, traveling at speeds ranging from hundreds of kilometers per second to over 1,000 kilometers per second. When CMEs head toward Earth, They can interact with the Earth's magnetic field, triggering geomagnetic storms. These storms, in turn, can induce electrical currents in the Earth's magnetosphere and ionosphere, affecting various forms of technology and infrastructure. One of the most concerning impacts of CMEs is their ability to disrupt the operation of satellites and spacecraft. The high-energy particles in the CME can damage satellite electronics, as well as affect their communication and power systems. The interaction of CMEs with Earth's atmosphere can also create brilliant auroras near the poles, which, while beautiful, indicate that the Earth is experiencing a geomagnetic storm. However, the effects of CMEs are not limited to the realm of space. The impact of CMEs on Earth's power grids is one of the most potentially devastating consequences of space weather. When a CME strikes Earth's magnetosphere, it can induce a phenomenon known as a geomagnetic induced current (GIC). These electrical currents can flow into power lines, transformers, and other parts of the electrical grid, overwhelming them and potentially causing widespread blackouts. The 1989 solar storm, which caused a massive CME to hit Earth, led to a 9-hour blackout in Quebec, Canada, leaving millions without power. A large-scale solar storm like the 1859 Carrington event, which was the most powerful solar storm on record, could cause far more widespread and prolonged damage to power grids, communications, and satellite networks across the globe. The extent of such damage could be catastrophic, requiring significant repairs and recovery efforts, and potentially costing trillions of dollars. In addition to power grids, space weather can affect other technological systems critical to modern society. Satellites in low Earth orbit, which provide services such as weather forecasting, telecommunications, and Earth observation, are particularly vulnerable to space weather. The radiation from solar flares and the charged particles in CMEs can disrupt their operation, causing malfunctions, degradation of sensors, or even complete satellite failure. Geostationary satellites, which orbit at a much higher altitude, are also at risk, although they are somewhat less affected by space weather events due to their position. However, intense solar events can still damage these satellites, especially their sensitive electronics, and create operational challenges for communication and data transmission. Space weather can also interfere with terrestrial-based systems, such as pipeline operations, aviation, and even the functioning of nuclear power plants. For example, solar activity can increase the levels of radiation exposure to passengers and crew aboard high-altitude flights, especially those flying near the poles. In extreme cases, it can even affect the health of individuals on the ground in certain regions of the Earth. Pipelines, particularly those in high-latitude regions, can experience corrosion when subjected to geomagnetic storms, as GICs induce currents that can corrode metal structures. While the likelihood of these extreme events is low, the potential consequences of a major solar storm are high enough that scientists and governments are taking steps to better understand and mitigate the risks associated with space weather. Scientists study space weather by observing the sun's activity through satellites and other instruments, such as the Solar and Heliospheric Observatory (SOHO) and the Parker Solar Probe, which provides critical data about the sun's outer layers. These tools allow researchers to monitor solar flares and CMEs in real time, providing early warning systems to help protect Earth's technology. Space weather forecasting has become an essential area of research, as it helps predict when solar activity will reach dangerous levels, allowing governments, businesses, and other entities to take precautionary measures. However, despite significant progress in space weather science, predicting the exact timing and intensity of solar flares and CMEs remains a challenge. The sun is a complex, dynamic system, and space weather forecasting is still in its early stages compared to weather forecasting on Earth. Improvements in forecasting techniques and technology, including better understanding of the sun's magnetic activity and how it drives space weather, are crucial for mitigating the risks associated with space weather events. In conclusion, space weather is a fascinating and dynamic aspect of our solar environment that has profound implications for modern society. Solar flares and coronal mass ejections, the sun's energetic burps, can have significant effects on satellites, communication systems, and even Earth's power grids. As our reliance on space-based technology grows, understanding and mitigating the risks of space weather will become increasingly important. With continued advancements in space weather monitoring and forecasting, we can better protect our technology and infrastructure from the disruptive effects of the sun's energetic activity, ensuring that we are prepared for whatever the sun throws our way. While the immediate threats posed by solar flares and CMEs are rare, the potential consequences of a major space weather event are so significant that ongoing research and preparedness are key to safeguarding modern civilization. Stay informed and prepared by keeping up with space weather updates. Understanding solar flares and CMEs is crucial as our reliance on satellite technology and power grids grows. Follow advancements in space weather science to protect our infrastructure from solar disruptions.